So, to study the system of particles and rotational motion, as we obtain the relation of omega with the velocity v, and now is the time to introduce a few more terms, like in the kinematics of the system of particles, or a single particle undergoing motion. We had the acceleration. So first of all, we define average acceleration as a, which is like here, this is the instantaneous acceleration of the particle at a time, which changes or which may remain constant independent of the time. So similarly, we know the definition of omega. Omega is just like A cross B, a vector defined like the in general vector A cross B, and this is in a direction perpendicular to the two vectors, okay, and so we define like A is equal to dv dt, so we define ddt of omega, which I can also write because omega is d theta or dt, so I can write this as this dt2, etc. Because this is a general thing, so if I write omega as omega x I cap plus omega y j cap plus omega z k cap, etc. in the system of coordinates that we have chosen, okay, then I can write this alpha is equal to alpha x I plus plus plus, like that. Now, if the axis of rotation is fixed for the body, if the axis of rotation is fixed, we may write a scalar relation, and that is the magnitude of the angular acceleration alpha is equal to d omega over dt. Both of them are scalars. So this is one of the quantities which is essential, which is required, which we will be using, and that is the angular acceleration. Now, let us define what is the equivalent of force in rotational dynamics, and that is what we call the moment of the force. We define it as the moment of the force, or it has got a singular name, and we call it the torque. The torque, which is represented by the Greek letter tau, I'm writing TAU. In northern India, tau means father's elder brother, okay. So I can define this tau as r cross f. Is a new vector which is perpendicular to the two vectors r and f, etc., etc., in keeping with the definition of A cross B, which we have done before. So I'll leave it at that, not emphasize too many things. Now, because it is a multiplication of the dimension of length with the dimension of force, so the force has the dimension of that dimension, you must remember, ml t minus 2 multiplied by L, I get ml square t minus 2, okay. And we know that this is also the dimension of work done or energy, which we express in joules. But in the system of units that we have adopted, SI system, this is chosen as Newton meter. But I prefer it to be meter Newton. There are some controversy about it. So this is also true, and to me this is also true as the unit in the SI system of units. So if you allow me to write this tau, the torque, as R cross F, then I can write the magnitude of this torque as tau is equal to R F sine theta, because A cross B magnitude is equal to AD sine of theta, where theta is the angle that the second vector makes in the string with the first vector. The second vector over here is F, and F makes an angle of theta, so I can write this as R sine of theta. And this can be expressed in two ways. This can be expressed in two ways. Either we can just take R sine theta in toto multiplied by the magnitude of the force, or I can multiply this F sine theta with R. In either case, in this case I can write this as R perpendicular into F, and in this case this is R into F perpendicular. So for the purposes of calculations etc., expressing things easily, we have this R perpendicular and F perpendicular. Now for example, I am writing here that R perpendicular is equal to R sine of theta is the perpendicular distance of the line of action of the force from origin. And similarly, F perpendicular is like this, and I'll just show it to you that if the two vectors as it goes in the original format of A cross B, where what is the direction of the resultant vector? The resultant vector is, if this is A and this is B, the direction of the resultant vector in the cross product is, if this is theta, then the C cap is out of the board. Need not emphasize time and again, but there is no problem if I do. Okay, and you remember that. So I said that the AB sine of theta is the magnitude of the what we make here, the parallelogram. And so I can have, if I drop a perpendicular here, this becomes equal to this was B, so this is B sine of theta, B sine of theta. And if I drop a perpendicular from here on up to on the second vector, then this becomes equal to, this is theta, this also becomes equal to theta. Okay, so this becomes equal to B A sine of theta. Okay, so this is A sine of theta, B sine of theta, etc., etc. You can just draw the diagrams properly and can understand. You will have to give a little bit of time. Okay, now we define another beautiful concept, attribute of this motion, and it is just like momentum, what we have in linear motion, in translatory motion, and I define it. The angular momentum is defined as the term that we use is L. Vector L is equal to R cross P. So this goes for the simple definition of this quantity. Of course, the dimensions is mLT minus 1. This has got the dimension of L into the mass into velocity, kilogram meter per second multiplied by meter gives us the unit in the NK system or in the system international. Naturally, this is a definition which I am obtaining again like before with a cross product of two vectors, and the magnitude of this vector is equal to L, which is equal to the magnitude of R multiplied by magnitude of P multiplied by sine of theta, in a similar fashion like what we have been doing. Like before, in the case of torque, what we did was that this can have two components. One I can write it as R sine of theta into P, and the other I can write as R into P sine of theta. So that I defined as R perpendicular here and P perpendicular over here. They have similar meanings of what I have done before. Now, if these are the conditions that exist, this set of conditions, if P is equal to 0, of course, this will be equal to 0. If R is equal to 0, then this will be equal to 0. And if none of the two, neither of the two is equal to 0, but instead the angle between the two is 0 degrees or 180 degrees, then sine of 0 degrees is equal to 0 and sine of 180 degrees is also equal to 0. Then what we find is that the magnitude here becomes equal to 0, or I can say that therefore the angular momentum under the conditions that we have just discussed is equal to 0. Now if I come here and redefine as it was L cross of P, then of course this is an equation. Whatever operation I do on the left hand side, the same operation I do on the right hand side, and what I am going to do is to ddt it, differentiate it with respect to time. So find the time rate of change of angular momentum, okay, and this will be simply ddt of R cross P. No problem. But I told you that if I have two functions which are multiplying each other, here the sign of multiplication that I have used is a generalized what we use in the computers. So I write, and this is from differential calculus, that if we have a function which is the product of two functions, function 1t and function 2t, okay, then I can write this as the differential of the first function into the second function plus first function into the differential of the second function. We can exchange the things. We can write this term before and this term after, no problem. But like what some of my friends, they have remembered it like this: the differential of the product of two functions is equal to the first function into the differential of the second function plus the second function into the differential of the first function, which is not of much use for we, the students of physics, because we are wedded to the concept of this order. The order should not be disturbed. So I have talked to you before, but now it is a specific case of cross product. So what I get is that ddt of L, the angular momentum, is equal to the dr dt, differential of the first function, into the second function plus the first function into the differential of the second function. Now we know the definition of velocity. The velocity is defined as dr over dt, okay, ddt of r, and because the linear momentum is defined as mass into the velocity, what we find is that dr dt into p, dr dt is what? It is velocity, and velocity cross momentum, and the angle between the two of them, because velocity and the momentum will be in the same direction, so the angle between the two of them is 0 degrees, sine of 0 degrees 0. Therefore this term dr dt cross p turns out to be equal to 0, and so what we are left with, this term, okay, here ddt of r cross p is equal to r into ddt of p, and ddt of p is defined as force, so I can just write that this is equal to r cross f, okay, and r cross f is defined as torque, r moment of the force. So if I just substitute here, then I get ddt of r cross p, or the angular momentum, equal to torque tau, and we can therefore write that this is dl dt, dl dt is equal to torque. So this relation that we obtain over here just shows that, establishes that torque is nothing but the time rate of change of the angular momentum, time rate of change of angular momentum. So from here we proceed for generalized systems. This is what we have done, and before also I defined torque and angular acceleration, etc., and this way we find that for a single particle system which is rotating about a point or an axis, these definitions show us the beautiful result that we get. And this result is akin to dp dt is equal to f. Okay, so we have dl dt, we have L is equal to r cross p, like we had. So things in this mechanics that we are developing are just similar. They draw from the mechanics of the translation of a body under various conditions. So after defining torque, angular momentum, etc., for individual system of a single particle about a fixed point, axis, etc., now I would like to extend the concepts that we have developed for a system of particles which comprises a rigid body, and if there are several constituents of that body, so I can write that the sum of all the angular momenta L1, L2 to Ln, okay, I can write this as capital L and write it briefly as summation for all the particles from 1 to n Li. And here, of course, Li is Ri cross Pi. The definition, Ri cross Pi. So if I write further, I can write that L is equal to I to n Li, and this by definition is Ri into Pi. R cross, I shouldn't have said into, no into. It is not an into, it is rather a cross, and we should bear in mind that whenever the cross product of two functions attributes is described, you must adhere to cross over here, no into. So now what I do is I differentiate this L, the total angular momentum, with respect to time. And like we have been doing before, therefore dl dt will be equal to ddt of sigma. Now I am writing, and here also I wrote I, and we mean that I varies from 1 to n. N can be any number. So in general ddt of sigma li, and I can take this function, this operation inside the summation, and it becomes equal to sigma I dli dt. But dli dt we have already defined earlier, that this is the torque. So I can write the same thing, equation, as sigma of all the torques that are there, of course, and the torque here we define as R cross F, Ri cross Fi. Now I can describe the force which has been responsible for the torque as the result of that force which acts in the body. So we find that Fi is equal to sigma Fi external plus sigma Fi internal. What does that mean? The summation of all the external forces which are acting in the system and the summation of all the internal pair of forces which are for one unit or the other unit, which is defined as in the third law F12 is equal to minus F21, which I'll shortly discuss to you. So what happens is that now I can write the torque. The equation of the torque, total torque, is equal to summation of all the individual torques, torque 1, torque 2, like that, which turns out to be like this, because torque is defined as, okay, like this. So I get this equation. Now, like in the case of forces, I write that the total torque on the system, torque is equal to torque external plus torque internal, where torque external is defined like this, Ri cross Fi external, and the internal one I define as Ri cross summation of Ri cross Fi internal. Now, according to the third law, I told you that force 1, 2 between any two internal is equal to minus F21, and this is one thing, but bear in mind that both these forces, they work along the same line. If it is like this is like this. If it is like this is like this. Okay, so I establish. We come to the conclusion that the torque can be of two types. One is the external and the other is the internal, which are defined like this. I have done it before, and we discussed that drawing from the third law, our conclusion, where F12 is equal to minus F21, both work, and both these work along the same line. So on the line joining any set of two particles 1 and 2, so we say that we understand that, we infer that the contribution of the internal forces to the total torque is equal to 0. Why? because the torque resulting from each action reaction pair F12 is equal to minus F21 equal to 0. So therefore what we find is that the torque, internal torque, net internal torque is equal to 0, and therefore the total torque turns out to be equal to the total external torque. So that now I can write from my description that rate of change of L, the angular momentum, ddt of angular momentum is equal to the torque external, total torque or torque external. Just like what we have before in the case of like we defined dp dt as total external force in a system of particles which we have for the translatory motion. Now the next item that we deal here is the conservation of L, the conservation of angular momentum, like the conservation of momentum. Of course, there we had, if the force is equal to 0, then dp dt was equal to 0, rp was a constant, and we could say the same thing here if the total external torque acting on the system is equal to 0, because that force was requisite for changing the condition of the body. Here the torque, application of a torque is essential for changing the angular momentum of the body. So dl dt is equal to 0, which means L is equal to a constant. Yani total angular momentum is conserved. Now I can write this total angular momentum L in the system that we have adopted for the XYZ coordinates. Okay, I can write it as the x component into I cap plus y component into j cap and z component into k cap. So now that L is a constant and these three components are in mutually perpendicular axes, making an angle of 90 degree with each other. So the cosine of, that is the result part of any one of them in the two directions is equal to 0. If I write that this Lx is equal to K1, Ly is equal to K2, Lz is equal to K3, so what do we infer? That the components are also conserved. The components of the vector L are the angular momentum in the x direction, y direction, z direction, they will also not change. If this external torque is equal to 0, no change in the external torque, I repeat, then that means dl dt, which defines the external torque, is also equal to 0, or if it is 0, so a ddt of what is 0? ddt of a constant is 0. So this constant I take here, that my L will be a constant. Let me tell you that in the case of the motion, translatory motion also, we had a P, then we could have a Px, we could have a Py, we could have a Pz, and in order that P remains unaltered, unchanged or conserved, then these values Px, Py, Pz, they should individually also not change. So that point I missed there. Now we take up a couple of examples. The first one is just the estimation of r cross f when r is given and f is given in the rectangular coordinate system And the second one is that if a body keeps on moving with a velocity, constant velocity in any direction, then for the system that we take coordinates, then we can show that r cross f remains unaltered, unchanged in the following examples. So let me take up a question, and the question is very simple, and the way to solve it I have already done for you. I have the position of a point, a certain mass which is located at the point r, which is defined as 1 I cap plus 1 j cap minus 1 k cap. Normally they will write it as I cap, j cap and minus k cap, but I include and do like that the numbers 1 should be included, and a force is applied on the system, 5I cap minus 3j cap plus k cap, nearly 1 k cap. So we are asked that from these data we are asked to calculate the torque, which I am defining as r cross f. You must do that, and also the magnitude of the torque. So a very simple exercise I have defined in the case of the cross product, that the cross product is where I write this as Rx, Ry, Rz, Fx, Fy, Fz, and I put these values over here, I, J, K, Rx, Ry, Rz, Fx, Fy, Fz, and the numerical values that I have taken, you can always substitute with other values of your choice, no problem. So this is equal to, in the first instance when I am taking this I, then I get this, J, this column is gone, I get like this, and K, I do away with this, and these two columns they appear. So when I write all these things and we make calculations, this minus this, this minus this, this minus this, I find that it turns out to be equal to minus 2I minus 6j minus 8k, etc. And of course then I calculate the value of torque as minus 2 square minus plus minus 6 square plus minus 8 square, which turns out to be equal to root over 104. It could be any value, it all depends upon the varying numbers here. You can make calculations, you can practice a bit, and of course I am writing here bit of controversy. Check it whether it should be Newton meter or it should be meter Newton. So I take up the second one, question number 2, which is a simpler question, and it appears in most of the texts, most of the books. In question number 2 is an interesting question, and that should be borne in mind, the result of this exercise. Now we are being asked to show that is to prove that the angular momentum L about any point of a single particle moving with a constant velocity v, same velocity which is described in Newton's first law, continues in its state of rest or of uniform motion. So here it is uniform motion. It remains constant throughout the motion. I have to show that. So it's very simple. From the definitions that we have, I am writing that L is equal to R cross P, and since P is equal to mv, so I can write this like this. And the exercise that we did before, we said Look here. Now, this is a mental picture of what I have made over here. This is the point P, and the point P, this is my R, and this is my velocity, which is the particle is moving in that particular direction. Often it's said that a particle is moving parallel to the x-axis, or parallel to the y-axis, or parallel to the z-axis, and it moves with a constant speed or velocity, whatever. What is the angular momentum? What will happen to the angular momentum of the system? Here, like I said, that I can write it as r sine theta into p, into, again I said, cross p. Okay, so when I am talking about the magnitude, it is r sine theta into p. Of course, this will remain constant, as it can be seen from here. This is the point O, about which you have to find out the moment, angular momentum. So you can see that this is r, and you can see that this is the direction of v. The angle between the two of them is theta. So this distance O to M, if I drop a perpendicular on the axis along which are the line of the motion of the particle, then this OM remains unchanged. This is the distance that we have, and therefore this is a constant. Even when the position of P changes, whatever, you can draw a line, maybe it is in this position, or maybe it is in this position, doesn't matter. Okay, whether the particle is moving in this direction or the particle is moving in the opposite direction, doesn't matter at all, because what matters is r sine theta. R sine theta is constant. So therefore, because this is constant, therefore the angular momentum associated with it will be constant, with it will be conserved. Okay, and we find that whatever the statement is here, we have been able to show that it is true, a true state. Sometimes I used to ask such kind of questions in a true-false kind of a binary. When I was at the college, Al-Baha Private College of Science, there we had to give one out of two choices. Anyway, that's not what is done in the MCQ kind of thing, but in interviews, of course, this kind of questions can be asked, and you should be ready to answer them. This is one thing. Another thing is that if you look into the system that we are dealing with, A cross B, and if you work out with the right hand curved system, then you will find, this is I am leaving to you, that L cap, the unit vector, is into the board, into your page, and try and enjoy that. In the coming lecture, I am going to talk about the principle of moments. The principle of moments, which I was taught as the law of moments, and we used to do experiments also in class junior classes, class 7th, 8th, etc. The principle of moments, because this is related with what is called the balance. Then I am going to talk to you about the center of gravity, which is similar to the center of mass. We will distinguish one with the other, etc., etc. And then one of the very important things I am going to discuss is moment of inertia. Moment of inertia, center of gyration, and thereafter the parallel and perpendicular axis theorem, this, that, maybe in the next couple of lectures. So we have been able to establish what is torque, what is angular momentum, what is the relation between two of them, what is angular acceleration, what is angular velocity, and major thing is that something which you used to think, how can it be, how can an angle be, or a change in the angle be vector quantity, but we have been able to show that the omega can be taken as angular, a vector quantity, so alpha, so other things, so thank you.